Welcome to this exercise where I'm going to talk about how to solve a root equation. Root equations are something like this here, where the x stands below some root expression, like here under the square root. To solve this, we have to get rid of this root expression first. So what do I do in this case? Well, first I have to isolate one of the root expressions on one side of my equation. For example, here I already have one of the root expressions on the left side. Then I have to consider which root do I actually take. In this case, the radicand is 2, because this is just the standard square root. So I have to then take the whole equation, both sides of the equation, to the power of 2. If there were the third root, so radicand would be 3, then I would have to take this to the power of 3. So power of is the inverse to the roots. So here I'm going to take both sides to the power of 2, getting rid on the left-hand side of the root sign. And on the right-hand side, well, I have two expressions with a minus in between. So I have to use second binomial form. So I take this squared, then 2 times this, giving me this expression, and then this part squared. Well, if I do it with this one here, I actually have this under the fraction and without the minus, because minus times minus is plus. This root gets away because the whole thing is squared. So I have here 1 plus x. Then I can bring all the stuff which is not the root expression on one side of the equation, keep the root expression term on the other side. So again, I'm going to isolate my root expression. Simplifying to this part, I can then also divide by any part which stands as a number in front of the root expression. So here I'm going to divide by 2, simplifying this even further. Again, the root expression I have is square root. So I'm going to take all of the two sides again to the power of 2. So I'm going to square left and right side. Right side, again, I get rid of the root expression, the root sign, having here 1 plus x only. Left-hand side, again, two terms with a minus in between. So again, second binomial form. So this squared minus this times 2. So 2 times x times 2 gives 4x. And then this squared gives x squared. So now I see largest term I have left is this one, or rather term with the largest exponent is this one. So this will be a quadratic equation. To solve a quadratic equation, I first bring all the terms on one side, and I do this in a way that the x squared has a positive sign. So I bring everything to the left side, looking like this. Then, since there is no number, no coefficient in front of the x squared, I can simply apply the PQ formula. PQ formula needs a p, that's the coefficient of the x, so minus 5, and it needs a q, that's the absolute term without any x, so here that's the 3. Then the formula gives two results. First part here is minus p half, so minus 5 halves, 2.5, plus minus for the two options. Inside here I have p half squared, minus 5 is minus 2.5, squared is 6.25. Then I'm going to subtract as well q, so q is 3, so I go with minus 3. So this gives me under the root 3.25, so I have 2.5 plus square root of 3.25 and 2.5 minus square root of 3.25, giving me in the end those two results, 4.3 roughly and roughly 0.7. Well, I have a root expression here, so I have to check whether those two solutions are also feasible. So I have to check whether I'm allowed to insert them in the original equation. Why am I doing this? Well, I'm only allowed to take a root, especially the square root. I'm only allowed to take the square root of positive numbers and 0, so not of negative numbers. Well, if I insert the first value here, I will get something of roughly 1.7. It's positive, so I can insert this on the left. If I insert this here, I get something of roughly 5.3. Again, positive, so I can insert this here. So none of the two root expressions pose any problem for the first result. If I go with the second, here I will have under the root roughly 5.3. Again, positive, no problem. And here I would have roughly 1.7. So again, also no problem. So both of these values are solutions to the equations, are feasible, valid solutions to this equation. Well, this then concludes this exercise, and I can just say goodbye and see you next time.